Hello, my name is Jeffrey McKelvey, and this is the third lab for Physics 2111, Section N01. The objective of this lab was to determine the mass of a black hole by analyzing the motion of an orbiting star and the net force we were able to glean using the law of universal gravitation, which we will discuss in a moment. My hypothesis was, if we use the position and movement data of two objects and the known mass of one object, then we can analyze the change in momentum over time, allowing us to find the net force and thus the mass of the second object. The mass of the star that I was given was 4.4322 times 10 to the 27th kilograms, and the position of my black hole was at 5 times 10 to the 10th power, negative 1 times 10 to the 10th power 0 meters. And my delta t, or time step, was 86,400 seconds, or 1 Earth day. The result that I found was that my black hole had a mass of 5.77 times 10 to the 31st power kilograms. In order to properly be able to perform this analysis, we must use the equation for universal gravitational force, which is as follows. The F net, or the net force, is equal to gravitational constant, which is approximately 6.67 times 10 to the negative 11th power, times the mass of the first object, times the mass of the second object, all divided by the absolute value of the distance between the two objects squared. We can rearrange this to get that the mass of the second object can be found by taking F net multiplied by the absolute value of the distance between the two objects squared divided by the gravitational constant multiplied by the mass of the first object. F net is indeed equal to the change in momentum over change in time, or dp dt, and it is important to note that neither net force, its parallel component, or its perpendicular component is equal to the perpendicular or parallel components of F net. They are equal but not the same thing. F net and its components are some of the net pushes and pulls within a system and on the system, while the change in momentum over the change in time and its various components are actually simply the measure of changes over time. Here, in this portion of our Python code, we can see how we calculate the delta x and delta y, which we use to find delta v. Here, we see v initial, v final, and then here we use this and multiply it by the star's mass to find the delta p, which gives us our change in momentum over our change in time, which is our time step. Here we see that the star's position is vector x and y with 0 in the z position, and we simply append this in order to re-evaluate and recalculate the mass at each point, which, although it all varies slightly between each position, there is a constant in our mass, in the first few digits of our mass, which, as you can see here, was 5.77. This here is the model created by the computer, where the green is the trail that the star has left, the black is the parallel component of the net force, the blue is the perpendicular component, and the yellow is the total F net that we get when we add them. Now, what if we were to imagine that the black hole were replaced by another black hole of an unknown mass, but the star remained upon the same trajectory at the same velocity? Would it be possible to find a mass for the new black hole that differed from the current one? And the answer is no. the mass would have to be the same. Otherwise, the net force on the star would be altered. And if the star travels along the same path at the same velocity within the presence of both black holes, their masses must be identical. So, once again, after going through all of this information, we can glean that by applying the law of universal gravitation, the mass of the black hole was indeed 5.77 times 10 to the 31st powers kilograms.